Hello, everyone. I am Suyash Gupta, currently a fourth-year PhD candidate in the Department of Statistics at Stanford University. Today, I'm going to talk about a measure called S-value that we have developed to evaluate stability of statistical parameters under distributional shifts. This is joint work with Dominic Rothenhosler from Stanford. We all are aware of replicability crisis in statistical research, which happens due to various reasons, like failure to account for multiple testing, publication bias, distribution shifts, etc. In this talk, I'll try to address replicability crisis that may happen in the face of distribution shifts. First, let us consider a very simple example. This is Anscombe's quarter dataset Anscombe had constructed, such that if we fit a linear regression model into each of these datasets, we get exactly the same OLS fit and the same p-values. However, the data set differ widely in distributions, and hence the regression coefficients or the OLS fit changes differently under distributional shift for each data set. Let us see how. So here I'm considering a covariate shift setting where we put more weights on right end of x-axis, like this. We see that under this covariate shift setting, sets 1, set 3, and set 4 quite stable. The corresponding regression coefficient has not changed much. However, for set 2, we see that the regression coefficient has drastically changed from positive to null or negative value. Hence, set 2 is quite unstable with respect to covariate shift. Let us look at more general shift. For example, in set 1, I've put more weights on these 3 points. And I see that by considering this particular shift, I can tilt the regression coefficient from positive to null or negative. So set 1, which was stable with respect to covariate shift, is no more stable under more general shift. If you look closely at set 1, it does appear that the data in set 1 has come from a linear model with a positive slope. Hence, considering more general distribution shift may make seemingly more stable parameters or regression coefficients look unstable. So considering more general distribution shift may be a bit conservative. Keeping this in mind, what are the take-home messages from the example we considered? So first, parameters can indeed change differently under distributional shift. And hence, findings with respect to parameters that are distributionally unstable may not replicate when distribution shifts. For example, in set 2, the finding that the regression coefficient is positive may not replicate if there's a covariate shift along x-axis, because in that case, the coefficient may be null or negative. We also saw that classical measures like p-values convey little about distributional stability of parameters because they were same for all the data sets. They couldn't distinguish this difference in behavior. Hence, it is useful to quantify the distributional stability of a parameter. Further, considering overall distributional shifts alone may be a bit conservative, as we saw, for example, in set 1. And often we don't expect all aspects of a distribution to shift. Hence, it is also can be useful to consider some less conservative shifts, like shift in certain marginal distribution of certain covariates, which we will refer to in this talk as directional shifts. For simplicity, I will consider a very simple setting in this talk. So I'll consider probability distributions which have finite support of size k. I will denote probability distributions by P and the corresponding weights that it takes on this finite support by W. And we will use this P and W interchangeably to denote probability distribution and weights, just for ease. So now let's define the stability value or S value that we developed to quantify the distributional stability of a parameter. So here we consider, say you have training distribution, some training distribution P naught, parameter theta, and without loss of generality, suppose theta under the training distribution is positive. We consider shifts in distributions with respect to KL divergence. We try to find the smallest shift in distribution with respect to KL divergence such that under this new distribution, the parameter becomes null. Then we define the stability value as exponential of negative of this smallest shift. Stability value, this value takes values in the range of 0 to 1. And S value of 0 means the smallest shift is actually infinite. That means it's never possible to tilt the parameter to null by considering any amount of shift. You can never tilt it to null. And a higher value of stability of S means lower value of the smallest shift. That means it's easier to tilt it to null, and hence more unstable your parameter is. So higher value of S means more unstable your parameter is, and lower value means it is more stable. Let us try to find this value for a very simple parameter, say mean of a random variable. So we consider distribution P0 with weights W0 and finite support with elements Z1 to Zk. We want to find S value for mean of the random variable Z. S value, as we have defined earlier, is essentially exponential of negative of the smallest KL divergence between the new distribution and the training distribution, such that under this new distribution, the mean is 0. Now we see that mean is actually linear in this new distribution or the underlying weights. It's a linear function. And the KL divergence is actually a convex function in this new weights. So we're essentially minimizing convex function under linear constraint, which makes the problem a convex optimization problem. And it turns out that the S value for mean in this case can be easily obtained by just minimizing the moment generating function of random variable Z. So that was S value with respect to overall shift. Now let's consider directional or variable specific S value, where we consider shifts in distributions, where we only consider shifts in distribution of certain covariates E, keeping the conditional distribution of other variables given this covariate E as fixed. So we are not allowing all aspects of distribution to shift, we're only allowing certain aspects of distribution to shift. Again, as before, we try to find the smallest shift in distribution, so that under this new distribution, we have the parameter as null. And of course, we only consider those distributions for which the conditional distribution given is fixed. And then we define the directional stability value as exponential of negative of the smallest shift or smallest radius. Before. Again, let's try to find S value or directional S value of simple parameters such as mean of a random variable. So here we are interested in finding directional S value of mean of random variable Z, where we only consider shift in distribution of some covariates E, keeping the other conditional distribution as fixed. As before, again, we are minimizing a convex function under one constraint that is linear. We saw that. And there's an additional constraint such that the conditional distribution is fixed. At least when E has finite support, the random variable E takes finitely many values, we can, it's easy to see that this constraint is just linear in U weights. And hence, the whole problem remains a convex optimization problem. And again, as earlier, it turns out that directional S value can be obtained by just minimizing the moment generating function, this time of conditional expectation of random variable Z given E. Now, we saw that since mean was linear in weights, it was easy to obtain its corresponding S value. And similarly, any parameter that are linear in weights, we can obtain the corresponding S value. So any parameter that can be written as a mean of some function of random variable are actually linear in weights. And for them, we can obtain S value just by minimizing the moment generating function of the function of the random variable. However, if the parameter is nonlinear in weights, then the problem becomes non-convex, and which is quite challenging. So we propose a majorization minimization based iterative algorithm. And to solve this and show that it always converges to a first order stationary point under certain assumptions. And this convergent solution, we can check if it's local optima by checking if it satisfies certain second order sufficient conditions. All right, coming back to the Anscombe squatted example, we saw that the OLS estimate was the same for all the data sets, and so was the p-values. Let's try to find S values. So the overall S value for S is 0.465, which is non-zero. So that means it is able to tilt it to 0 under general shift, which we already saw. It was able to, we were able to tilt it to 0. However, we will never be able to tilt it to 0 if we only consider covariate shift, which is indicated by the directional S value, which is 0. For set 2, both overall and directional S value is quite high and non-zero, so it is distributionally unstable with respect to all kinds of shifts. However, set 3 and set 4 are quite distributionally stable with respect to any kind of shift. We also, here we plot the minimum and maximum achievable value of the regression coefficient for each data set within a given amount of shift in distribution. Here we consider shift in marginal distribution of the covariate. We can also consider shift in overall distribution as well. So looking at this plot gives us a deeper idea of distributional stability of the parameter. So if you look for set 2, the parameter changes widely with respect to shift in distribution, and hence it's quite distributionally unstable. Whereas for other sets, set 1, set 3, and set 4, the change is not much. And then there's quite distributionally stable, at least under covariate shift. Coming to real data, here we consider wine quality data, which has two subgroups, red wine and white wine. We had response as wine quality on a scale of 1 to 10, and covariates as some continuous features of wine. Sorry. So we can look at distributional stability of different regression coefficients for different covariates. So here we look at the regression coefficient of covariate pH. And here we measure, again, find minimum and maximum value of this coefficient within a given amount of shift in marginal distribution of any given covariate. So I'm considering only shift in distribution of a given covariate. And we see that with respect to shift, certain directional shift is more unstable than other. So we are going to use this information soon for a next task that I'm going to talk soon. Let's just keep this information in mind for now. Here we consider another data set, which is national supported work demonstration data set. Here we consider average, which intended to evaluate average treatment effect of an employment program on trainee earnings. And we again plotted this, we try to understand distributional stability with respect to different directional shifts. And we saw that average treatment effect was quite unstable with respect to shifts in distribution of age, education, and pre-intervention earnings. Again, let's keep this information in mind. We're soon going to use it. So far we have seen that a parameter can be distributionally unstable with respect to various shifts. So what if a parameter is unstable? So if a parameter is unstable, it takes different values as if distribution shifts, right? So can we give better estimate of parameter under a target shifted distribution of interest? But the challenge is that we can collect very limited data from this new distribution, say certain moments of some covariates. So we show that if we can collect moments of those covariates along which the parameter was quite unstable, we can give a much better estimate of parameter under the shifted distribution. And this is where we are going to use this information along which covariates the parameter was quite unstable that we have seen in previous plots. So the idea is we want to guess the new distribution with minimal information, just say moments of certain covariates. So the intuition is that we try to find a reweighting of the training sample, such that under this new reweighting, the moments of the selected covariates match that of moments under the new distribution that we have collected. And since there can be a lot of different choices of reweighting, we try to find the reweighting that is closest to the training distribution and still help matching the moments. And under this new reweighting, we recompute the parameter. And on wine quality data set, we see that the parameter, this procedure gave better estimates of parameter under shifted distribution than under training distribution. Similarly, on this national supported work demonstration data set, the parameter transfer method gave better estimates of parameter under shifted distribution than under training distribution. We can also consider model transfer. So a predictive model can also be unstable with respect to distribution shift. So suppose you have training distribution, you collect data, you train a predictive model, but that model may not perform well on data from a new distribution. So can we obtain a better model for this new distribution? And again, the challenge is that we can only afford to collect very few supervised samples from this new distribution. And hence they may not be enough to train the model from scratch for this new distribution. So can we somehow use this existing data set and few supervised samples from shifted distribution to train a model that performs well on the shifted distribution? The idea is again simple. We try to find a reweighting of training samples such that the model trained under this reweighting gives a lower desired risk on this new test set of few supervised samples from new distribution. And again, we regularize by finding distribution that is closest to the training distribution, such that the model trained under this new distribution has a lower desired risk. And we can choose this threshold, desired risk, via cross-validation. So we did use this model transfer technique on wine quality data, where we tried to transfer the predictive model from, say, training set, which consisted of all white wine, to test set, which consisted of all red wines. There's a natural distribution shift between these two data sets because the two wines are very different. And using our model transfer technique, where we use only a few supervised samples from red wine, we were able to obtain a predictive model that performed much better on this test set than the model trained under training set alone. So to that end, we can conclude my talk. So we saw that shift in data generating distribution is inevitable, and due to which statistical knowledge may fail to generalize. In this talk, we try to develop measures to understand distribution instability and further suggested steps to deal with it.